Hello students, and welcome to your first lesson from Chapter 10. Chapter 10, we get into a whole bunch of ideas of counting principles, permutations, the idea of some probability, and as we get into the next chapter, we'll be talking a little bit more about some statistics, but basically looking at probabilities of various events is really the gist of Chapter 10. So the first thing we need to talk about is the idea of a permutation, and a permutation is an ordering of n objects. All right. The one thing that's really important to recognize in a permutation is it's an ordering. All right. And so as we talk a little bit about this idea of permutations, the order matters. Okay. The order does matter in a permutation. All right. Now, a factorial is a way to represent a repeated multiplication, not a repeated multiplication, but basically we use the exclamation mark to say we want to multiply the numbers from n all the way down to 1. All right, so factorial, for example, 5 factorial would be the same thing as 5 times 4 times 3 times 2 times 1. All right, now there's an easy way to do that on your calculator, which I will be showing you a little bit later on in the lesson, but for right now, we just have to understand that that's what that factorial means. All right, so those are the two key vocab things that we needed to talk about for this lesson. Let's take a look at how that applies to our content. All right, now the first thing is this idea of the fundamental counting principle. It says two events. If there are two events that we're concerned with, it says if one event can occur in m ways and another event can occur in n ways, then the number of ways that both events can occur is the product of m times n. All right, this is called the fundamental counting principle. So, for example, if you had, 5 different events that could occur one way and 4 different events that could occur a different way, that would be 5 times 4. That means there are 20 different ways that these events could occur. And again, we'll get into some real examples in just a few minutes. So when we get into 3 or more events, for 3 events, it would simply be m times n times p, and they use m, n, and p. But if there were more than 3, like 4 or 5 or 6, again, it just kind of depends on what variables we use. All right. So again, it's the probability of, or the possible number of ways that something could occur ends up being the product of each of the ways each individual event can occur. All right. So let's take a look at how that applies to the first example, example number 1, and taking a look at some pizzas. It says you're buying a pizza, you have a choice of 3 crusts, 4 cheeses, 5 meat toppings, and 8 vegetable toppings. How many different pizzas with 1 crust, 1 cheese, 1 meat, and 1 vegetable can you choose? Now again, the key here is that you cannot have a pizza with ham and bacon, which happens to be my favorite. You can only have 1 meat, all right? And so using the fundamental counting principle to find the total number of pizzas that we can create from this series, again, you can have 3 different crusts, you can have 4 different cheeses, and we don't want to sit here and kind of write every possibility down because this is going to take us a little while. What we're going to do is we're going to multiply the number of crusts, which there are 3 of them, the number of cheeses, which there are 4, the number of meats, which are 5, and the number of vegetables, which is 8. So this becomes there are 3 different crusts to choose from, there are 4 different cheeses to choose from, there are 5 different meats to choose from, and 8 different vegetables. And so 3 times 4 times 5 times 8 comes out to 480 different pizza combinations that I can make. All right, and again, we don't want to make a table and a chart and start writing all of these down because this will take us an extraordinary amount of time. Instead, we just multiply the number of combinations, the number of possibilities for each, and that tells us the total number of outcomes that we can have. All right? So on the top of the next page, there's a checkpoint example. Let's kind of work through this together. It says if the pizza crust was not a choice in example 1, how many different pizzas could be made? So again, going back to example 1, we no longer have the choice of crust, but we still have the 4 cheeses, we still have the 5 meats, and we still have the 8 vegetables. And so this is 4 times 5 times 8, which is 160 different possibilities. All right? Okay. So let's take a look at another example then. Example number 2 says using the counting principle with repetition. All right. A town has telephone numbers that all begin with 329 and are followed by 4 digits. How many different phone numbers are possible? A, if numbers can be repeated, and B, if numbers cannot be repeated. All right? So if numbers can be repeated in part A, there are 10 choices for each digit. Okay, their phone number could be 329-0000. Could be 329-0001. 329-0002, etc., etc. There's a whole bunch of different phone numbers. But there are 10 different digits you can choose for the first. There are 10 for the second, 10 for the third, and 10 for the fourth. So 10 times 10 times 10 times 10 is the same thing as 10 to the fourth. And so the fundamental counting principle says that we can have 10 times 10 times 10 times 10, or 10 to the fourth, which is 10,000 different phone numbers. All right. So there are 10,000 different phone numbers that we can come up with, starting with that 329. Now, if you can't repeat digits, for example, you would have to have 329 1234, 329 1235, etc., etc. I mean, obviously, I kind of started in the middle there, but you can have all kinds of different numbers. The key is that these two numbers cannot be the same. None of these digits can be the same. So it says if you cannot repeat the digits, there are still 10 choices for the first number. This first number right here could be one of 10 different choices. Well, the second number, since I can't repeat, there are only 9 choices left for the second number. And if I've used, for example, a 1 and a 2, then I have 8 different choices for this number. So there are 8 different choices for the third digit. And as you can guess, there are only 7 different choices left for the fourth. So the fundamental counting principle then says this is 10 times 9 times 8 times 7, which is, I have that number somewhere, 5,040 different combinations. All right. Now, we had 10,000 phone numbers when we can repeat numbers, and only 5,000 when we can't repeat numbers. So that's pretty big discrepancy, right? All right, let's take a look at this idea of a permutation. As I talked about before, this idea of a permutation says that the order matters, and that's the big thing I need to continue to drive home, is that order matters. Okay? It won't matter in our next lesson when we start talking about choices, but for permutation, the order does matter. It says 8 teams are competing for a baseball playoff. In how many different ways can the baseball teams finish the competition? All right. And then in part B, in how many different ways can 3 of the baseball teams finish first, second, and third? All right. And so in the first part, part A then, it says how many different ways can the baseball teams finish the competition? Well, there are 8 choices for the first team. There are 7 choices for the second team, 6 for the third, 5 for the fourth, and so on. So you get all the way down to 8th place, and there'll only be 1 team left, because you can't be a team that's in first place and 5th place, right? So that ends up being 8 factorial. And when we say 8 factorial, all that means is it's the product of 8, 7, 6, 5, 4, 3, 2, and 1. All right, so we want to multiply all those numbers together, which is 40,320. All right? All right, and again, that assumes there are no ties and that each team has to be a different team, because obviously you can't be in 2 different places at once. All right, taking a look at your graphing calculator then. On your graphing calculator, you can use under the math menu, and way over here to probability, you'll see that there is a exclamation point which represents factorial. Now, if I simply press factorial, it's going to bring up the previous answer. So we have to tell it we want 8 factorial. So press 8, math, over to probability, which is my option over here on the right, and then we're going to scroll down to option number 4, and that gives us 8 factorial, which is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we don't have to type all that in, we can simply use 8 factorial on our graphing calculator. All right. Now, in part B, it says how many different ways can 3 of the baseball teams finish first, second, and third? All right. So if I'm taking a look at that next piece, it says any of the 8 teams can finish first, right? So again, randomly selecting, if we went into the season prior to, we didn't know anything about records or anything like that, it says any of the 8 teams can finish in first place, and then there are only 7 teams left that could be in second place, and obviously only 6 teams left that can be in third place. And so again, using our fundamental counting principle, that says that there are 8 choices for first, 7 choices for second, 6 choices for third, and 8 times 7 times 6 comes out to 336. We cannot use a factorial for this because I'm not getting times 5, times 4, times 3, times 2, times 1. All right? So we're simply just going to do 8 times 7 times 6 in our calculator. All right, top of the next page then. Let's talk a little bit about this idea of permutations. All right, it says the permutation of n objects taken r at a time. So if this is n is the total number of objects, all right, n is the total number of objects. So that's the total, and then r is the number we get, or the number we choose, or however you want to say that. But it's the number of objects being taken at a time. So, for example, the last problem we just worked on, we had 8 possible teams, and we were choosing 3 at a time. All right. So rather than go through that possibility, we want to take a little bit of a look at this idea of this permutation. If I'm choosing n objects and r at a time, all right. It says the number of permutations of r objects taken from a group of n distinct objects is denoted by n permute r. And so we call this n permute r, meaning the total number of objects, permutation or permute r, where r is the number of choices that I'm taking. All right, and the formula for that says n permute r is n factorial over n minus r factorial. Again, this is the total number, this is the number we're choosing. So it says find permutations of n objects taken r at a time. So you have 6 homework assignments to complete over the weekend. However, you only have time to complete 4 of them on Saturday. In how many orders can you complete 4 of the assignments? All right. So we have 6 objects permuted 4 at a time. All right. So 6 objects permuted 4 at a time, or taken 4 at a time, says we've got 6 factorial over 6 minus 6 minus 4 factorial, all right, because again, the number of choices is 4, and so the number total is 6, so it's 6 minus the number of choices. This becomes 6 factorial over 2 factorial. Now remember, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, right? And 2 factorial is simply 2 times 1. So if you think about this being a fraction, okay, 1 cancels with 1, big deal. 2 cancels with 2. And this ends up being 6 times 5 times 4 times 3. And 6 times 5 times 4 times 3 ends up being 360. Okay, so there are 360 different ways that you can complete those assignments, all right? Maybe you did math, English, science, and social studies, but you skipped health and, I don't know, whatever your other classes are, okay? All right, try a couple of checkpoint problems. Go ahead and pause your video here. I want you guys to try these, and let's see how they go. We'll be right back with solutions for you, okay? All right, checkpoint number 2, it says how many different 7-digit telephone numbers are possible if all of the digits can be repeated. So 7-digit telephone numbers, all the numbers can be repeated. So you could have the phone number 111-1111, right? You could have 222-2222, and any combination of those. So there are 7 different digits, and there are 10 possibilities for each of those 7 digits. So the first digit, you have 10 possibilities. The second digit, you have 10. The third, you have 10, and so on and so forth. So that means there are 10 to the 7th power possibilities. And 10 to the 7th power becomes a 1 followed by 7 zeros. Oh, I ran out of space here. 3, 4, yeah, it ends up being 10,000. 10 million different phone numbers, all right? 10 to the 7th, whatever that comes out to be, 10 million. And again, that's if numbers can be repeated, all right? In example number 3, how many different ways can the teams finish if there are 6 teams competing for the playoffs, all right? Well, if there are 6 teams competing for the playoffs, that means that there are 6 different ways that you can choose the first place team, all right? There are 5 different ways to choose the second, 4, 3, 2, and 1. So essentially, your first place team, there are 6 combinations. There are 5 combinations for you, because again, there's only 6 that we're worried about. You're only worried about the first 6 places. So there are 6 possible teams that can be in first, 5 that can be in second, 4 that can be in third, and so on and so forth. So it ends up being 6 factorial, which is 720 different combinations, all right? And then finally it says you have a list of 9 chores to complete, and how many orders can you complete 5 of the chores? So again, this is 9 permute, can't write and talk at the same time, 9 permute 5. So we're permeating 9 choices over 5 ways to choose them. So 9 permute 5 ends up being 9 factorial over, and on the bottom this ends up being 9 take away 5 factorial. So this is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. All over 9 minus 5, which is 4 factorial, which is 4 times 3 times 2 times 1. These cancel, 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 and cancel, and I'm left with whatever 9 times 8 times 7 times 6 times 5 is. Okay? And that comes out to 120 different ways. All right, now, I'm finally ready to let the cat out of the bag on how to do this permutation bit. All right, we need to choose 9 permute 5. Okay, 9 permute 5. Let's write it the right way. All right, now let's go back over to my graphing calculator real quick. And I want to put 9 permute 5 in my graphing calculator. So I'm going to turn this baby on. I'm going to type my 9 in first, and then I'm going to hit math. Move this out of the way. Math, slide over to probability, and you'll see NPR here. That means n choices permuted r ways. So this is NPR. So 9 NPR, and we want to choose 5 chores. Okay, 9 permute 5 ends up to 15,120. And you remember that down below, down here, hopefully you got 15,120. All right, so that's how you do it on your graphing calculator, but I wanted you guys to recognize how to do it first before I showed you the buttons on the calculator to do it. Okay? All right, let's take a look at permutations with repetition. All right? This is a little tricky, but I think it should make a lot of sense once you kind of take a look at these. They're missing a factorial in here, so we need factorial here. So if you'll type that in there or just jot that in there. It says the number of distinguishable permutations of n objects where one object is repeated s1 times, another is repeated s2 times, and so on is as follows. N factorial over s1 factorial, s2 factorial, etc., etc. Again, these are the things that are repeated. All right? Now, you might be asking, what does distinguishable mean? Well, distinguishable means those combinations that you can distinguish between. All right, so when you take a look at example 5, this should make a little bit more sense when we talk about the word distinguishable. But if it still doesn't make sense to you, we can certainly talk about it in our next class meeting. All right, it says find the number of distinguishable permutations of the letters A, E, V, E, N, and the letters B, C, A, L, blah, 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 spelling California. All right, so even has 4 letters, right? All right, and of that, 1 letter is repeated. All right, one of the letters, the letter E, is repeated 2 times. All right, so we can have E-V-E-N, or I can flop these two and still make it E-V-E-N, and those would not be distinguishable repetitions, right? We wouldn't be able to distinguish between whether or not this E was first or this E was third. That wouldn't be a very distinguishable combination. Now you could have V-E-E-N, not like that's a word or anything, or you could have V-E-E-N, where this E and this E were distinguishable, but if they're not distinguishable, you can't tell the difference between them. That's why it means that's why it talks about distinguishable representations. Okay, so basically, again, it says so the number of distinguishable permutations is 4 factorial over, and again on the bottom we're going to multiply all the different combinations and how many times they're being repeated. So we have 1 letter that's repeated twice, and so that's 2 factorial. All right, 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1. Cancel, cancel. I'm left with 4 times 3, which is 12. So there are 12 different combinations of the letters E, V, E, and N. All right. So maybe if you're playing Scrabble, this might be helpful for you. All right. Let's take a look at the California one. All right. Altogether, the word California has 10 letters, of which there are 2 letters that are repeated in this case. The letter A and the letter I are both repeated. Each of those is repeated 2 times. So the number of distinguishable permutations should be 10 factorial over the product of each of the repeated terms and how many times it's repeated. So I have 2 different letters that are repeated twice. If I had a letter that was repeated 3 times, I'd do 3 factorial. But since it's 2 factorial times 2 factorial, this ends up being 10 factorial, which is 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, and 1. All of that over 2 factorial, which is 2 times 1 times 2 times 1. Well, the ones really don't matter. 2 cancels with 2. And let's just say 2 goes into 4 twice. All right, so I end up with this kind of a mess right here, right? Either way, it's 10 times 9 times 8 times 7 times 6 times 5 times 2 times 3, because again, we're reducing. And altogether, you end up with approximately 907,200 distinguishable combinations of the letters California. All right. Now again, because there's a repeated I and a repeated A, we're going to do there are two different letters that are repeated twice. All right. So let's take a look at the checkpoint down below for tomorrow and yesterday. Try these two examples for me. We'll be right back with a solution. All right. So tomorrow has 1, 2, 3, 4, 5, 6, 7, 8 letters. So 8 factorial. And then how many different letters are repeated? Well, in this case, we have the letter O, which is repeated 3 times. And we have the letter R, which is repeated 2 times. All right? And so this becomes 8 factorial over 3 factorial times 2 factorial. All right? Because we have the letter O repeated 3 times and the letter R repeated 2 times. Okay, so this is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 3 times 2 times 1 times 2 times 1. Because again, that's 3 factorial and that's 2 factorial. So let's just go here and get rid of those. Let's get rid of the 3. The 1 doesn't really matter. And 2 goes into 4 twice. And so now we would just multiply 8 times 7 times 6 times 5 times 2. And so altogether you end up with approximately 3,360 different combinations of those letters. All right. In yesterday, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. So 9 factorial over. And then we have the letter E that's repeated twice. Right? Any other letters repeat twice? Well, sure, the letter Y repeats twice, so we have Y repeated twice. And so this is 2 factorial times 2 factorial, which really is essentially just 4, right? Because 2 times 1 times 2 times 1 is just 4. So this is 9 factorial over 4. And maybe an easier way to do that is to slide over to my graphing calculator and do 9 factorial. I got to move that, sorry. 9 factorial divided by 4, and I get roughly 90,720 possible combinations. All right. So that concludes lesson 10.1 on permutations.